In this video, we will look at arithmetic progressions, or AP in short, which is a series where consecutive terms have a common difference between them. Some examples of APs are listed here. The common point between these three sequences are that between the consecutive terms in the same sequence, we would add or subtract a certain value. For example, in this first sequence, every subsequent term increases by 3. In this second sequence, every subsequent term decreases by 4. And in this third sequence, every subsequent term increases by d. In every AP, we can define two values. The first value is called the first term, a. The second term is the common difference, d, which is the constant increment between subsequent terms in the sequence. Once we define the first term and common difference of an AP, the terms in the AP will be u1 equals to a, u2 equals to a plus d, u3 will be equals to u2 plus another d, which means a plus d or a plus 2d, and u4 will be a plus 3d. And if we rewrite all of these terms, we will get a plus 1 minus 1 d, a plus 2 minus 1 d, a plus 3 minus 1 d, a plus 4 minus 1 d. And from here, what we can observe is that eventually, if we look at the nth term, it will be a plus n minus 1 d. And hence, this is the value for the general term of an AP. And in this formula, you can think of n as the position of the term in the sequence. Other than finding the individual terms of the AP, we can also find the sum of n terms in an AP, which we denote using Sn. And therefore, Sn will be equals to u1 plus u2 plus u3 all the way until un. However, this form is not very elegant, and we will want to derive a more concise way of calculating this sum. If we write Sn as a for u1 plus a plus d for u2 and so on until the last two terms, which is a plus n minus 2d, and finally a plus n minus 1d, and rewrite this entire sum in the reverse order. Sn will be equals to a plus n minus 1d plus a plus n minus 2d, and so on until we have a plus d and finally a. Now, if we are going to add these two sums up, we know that the left hand side will become 2Sn, and on the right hand side, we can see that every group over here, they will give us the same exact sum of a plus n minus 1 d. And therefore, since there are n terms of them, 2Sn will be equals to n multiplied by a plus n minus 1 d. And since this is our un, we can say that 2Sn will be n multiplied by a plus un, which means that Sn will be equals to n over 2 a plus un. And thus, this is the formula for calculating the sum of an AP if we know the first term and the last term. Also, since we know that un is equals to a plus n minus 1 d, we can also rewrite Sn by replacing this un with a plus n minus 1 d to give us n over 2a plus n minus 1 d. In Sn, you can think of the n here as the number of terms that are being summed, which is different from the definition of n in Un, which we have learned earlier, where n is the position of the term in the sequence. Also, given Sn, we can find Un by subtracting Sn with Sn minus 1. In example 1, we are now required to find the sum of the first 100 odd numbers. So we can see that it is going to be an AP because we have 1 plus 3 plus 5 plus 7 and so on. And in between every term, it is a constant difference of 2. And the first term over here is 1. Therefore, we know that for this AP, A equals to 1, D equals to 2, and the number of terms to be summed will be 100. So we can say that the sum equals to n over 2, 2a plus n minus 1 d, which becomes 100 over 2, 2 times 1, plus 100 minus 1 times 2. And this will give us 10,000. Example 2 is a case of a composite kind of question where there is an AP within another AP. So for this, the definition of n within Un and Sn will be very important. So if we look at the first sequence, Un will be equals to 2, 4, 6, 8, and so on. And eventually we will have a term which I will call it U capital N, which is the term the question wants me to find, the last member of the n bracket. Note that if I want to find out what is this term, I can make use of the formula a plus n minus 1 d. But I will want to find it in terms of small n rather than capital N, so I will need to find out an expression for n. And how do we obtain this expression? We will have to look at the second AP that is involved in this question, and I'll call it Vn. It will be 1, 4, 7, 10, and so on. And we can see that the position of this term capital N is going to be the sum of all the terms over here until the n bracket. Therefore, what it means is capital N is going to be 1 plus 4 plus 7 and so on until the nth term, which is the sum of an AP, and we can calculate it very easily. N over 2, 2a plus n minus 1 times d, which is 3. And we can simplify this into n over 2, 3n minus 1. And once we have this value of capital N, it is going to be the position of the term that we are interested in. And therefore, the term that we are interested in will be Un equals to a plus n minus 1d, where a is 2 plus n. I'm going to use the capital N now. N over 2, 3n minus 1 times d, which is 2. And I will end up with 3n squared minus n. Sometimes we are required to prove that a certain given sequence or series is an AP. And to prove so, we have to make use of the property of an AP. That is, the difference between consecutive terms must be a constant. Thus, for any given sequence Un, we simply have to find Un minus 1 and the difference between them. If this difference is a constant, then the given sequence is an AP. However, do note that we have to make use of the general term Un minus 1 in order to show that it's an AP. We will never be able to make use of specific terms. For example, U3 minus U2 equals to 5, U2 minus U1 equals to 5. And because both of these are equal, we say that the sequence is an AP. This does not work this way because we do not know whether subsequent terms, for example, u4 minus u3, is it going to be equal to 5? Therefore, we will have to make use of these general terms which ensure that all the differences between all the terms within the given sequence is going to be a constant. In example 3, we are given the sum of a series and asked to show that this sum actually comes from an AP. So from earlier, we learned that in order to show that a certain sequence is an AP, we need to show that un minus 1 is a constant. But we are not given un now. However, we can find it very easily because we know that un must be equal to sn minus 1. And therefore, if we do a substitution, we will get 3n squared plus k minus 3 times n. This is sn minus 3 times of n minus 1 squared plus k minus 3 times n minus 1. Now I'm going to regroup them and factorize in order to simplify it rather than expanding everything. So grouping this and this together, I will have 3 times of n squared minus n minus 1 squared, and grouping this term together with this term, I will have k minus 3 multiplied by n minus n minus 1. So the reason for doing so is because in this term, I can make use of the properties of a squared minus b squared, which is equals to a plus b, a minus b. And this gives me 3 multiplied by n minus 1 multiplied by n plus n minus 1. And this second term over here is simply just k minus 3. And therefore, I will end up with 6n plus k minus 6 for un. Now that I have found un, I will need to find out the difference between un and un minus 1. So un minus 1 will be 6n plus k minus 6 minus 6n minus 1 plus k minus 6, which eventually will give us a 6. And since this is a constant, we know that Sn is from an AP. And we also need to find out what are the first term and common difference of this AP. The first term will be U1. We can substitute 1 into this n over here. And this gives us k. And for the common difference d, it will be equals to un minus 1, which is 6, as what we have found earlier.